Hi, we are now looking at section 4.6, which is about modeling with exponential and logarithmic functions. Many processes in our world we use or can be modeled by exponential functions or logarithmic functions. We in this class are only going to discuss exponential functions, and the processes like population growth, radioactive decay, heat diffusion, spread of disease, and in many others we see exponential function working. Okay. So let us start with a look at how the bacteria grows. So if a bacterium splits into two bacteria in a day, then we would have this situation. On day 1, so I'm going to write here t, so time is in days. So on day 0, the initial time, we have 1 bacteria. So let me say n denotes the number of bacteria. Then we have 1 here. On day 1 there will be 2. On day 2 there will be 4. On day 3 there will be 8, because we are always talking about double the previous day, double the amount on the previous day. So now it will be 16, 32, 64, and keeps going. Now this we are assuming that no bacteria dies and the population keeps on growing forever. So these are not exactly what happens, but for the sake of simplicity, we assume this in the beginning. Later on, when you take higher courses in math, you will see that the model has been redefined or has been made more close to the actual conditions in population. Right? Okay, So this population, we can model it by the function f of t is equal to 2 to the t. Why? Because if you note these numbers, they are all powers of 2. So 4 is 2 squared, 8 is 2 cubed, 16 is 2 to the 4th, 32 is 2 to the 5th, this is 2 to the 6th. So what will be the next one? 2 to the 7th, and so on. And the initial ones, I can say this one is 2 to the 1 and this is 2 to the 0. So if you look at the powers, the numbers in the powers are the same as number of days. So when we have a 0 day, the number of bacteria is 2 to the 0, which is 1. On day 1, the number of bacteria is 2 to the 1, which is 2, and so on. So that's why we can model it by the function 2 to the t. Now, if in the start we instead of 1 bacteria, we have some other number. So let's say, for example, if we start with 10 bacteria, then the population growth model can be written as f of t equal to 10 times 2 to the t. Why? Because let's say, let me put the number here with a different color. Okay, so with the second model, or with the initial population being, so here the n of 0 means at time t is equal to 0 we had 1. Now if we have n of 0 equal to 10, means initial population is 10, then what will happen? On the day 0 we will have 10 bacteria. On day 1 we will have 20 bacteria. On the day 2 we will have 30? No, it will be double of the 20, which means 40. And then on day 3 we will have double of 40, which means 80, and so on. So here you will have 160, 320, 640, and so on. So if you notice here, this can be thought of as 10, this can be thought of as 10 times 2, and this is 10 times 4. The next is 10 times 8, 10 times 16, and so on. So if you notice, this is 10 times 2 to the power of t. So that's why we can model this a function with initial amount 10 can be modeled as 10 times 2 to the t. So if we have an initial amount of 100, then the model will be 100 times 2 to the power of t. So if the initial amount is represented by n of 0, then the formula will be n of t is equal to n of 0 times 2 to the t. Most often we represent or we use the symbol n sub 0 for n of 0 means the initial population. So our formula can be written as n of t is equal to n sub 0 2 to the t. Okay. So exponential growth, doubling time. Now this is just like you don't have to memorize this formula. You should be able to, in the given situation, you should be able to find out what whatever is required. In this case, it says if the initial population is n sub 0 and the doubling time is a, then the size of the population at time t is this. So if you know the doubling time, and if you know that it's a bacteria population, so then you will get the because bacteria divides into 2. Not everything will generate or will deliver 2 exactly 2 of offsprings every time. So this is a special case. Okay. So A and T are being measured in the same units of time, which can be minutes, hours, weeks, days, years, or whatever. Okay, so let's look at example 1 here. So it says under ideal conditions, a bacteria population doubles every 4 hours. Initially, there are 1,000 bacteria in a colony. Find a model for the bacteria population after t hours. So we already kind of know it's going to be this model because we know the doubling time. So we here know doubling time is equal to we have denoted by a, which is equal to 4. Therefore the n of t, your model will be n of t equals n sub 0. What is n sub 0? Maybe I'll write that. N sub 0 here we know is 1000. So your model will be the model will be n of t equals 1000 2 raised to the power t over 4. So this will be the model. Okay. Now the B part says how many bacteria are in the colony after 24 hours. So basically it's asking when t is 24 hours, n is equal to question mark. So what do? You just plug in 24 for t. So in other words, or n of 24 equals question mark. That's what this question is asking. So how can we do that? Basically we just need to find n of 24, which will be equal to 1000 times 2 raised to the power 24 over 4, which is equal to 1000 times 2 raised to the power 6. Now we calculated 2 raised to the power 6 up in the beginning, so this will be 1000 multiplied by 64 or 64,000. Makes sense? Okay, so the next thing is now we are going to write it in words. So often when the question is in worded question, answer should be in the same format. And so we have 64,000 bacteria. So we'll say there will be, or you can start with more better answer will be, after 24 hours there will be 64,000 bacteria. Okay, the next part is asking after how many hours will the bacteria count reach 1 million. So slightly different question, but we will use the same formula, of course. What was our formula with whatever the model was? Remember, it is n of t equals 1000, which we can use, remember the initial amount, and then we have 2 raised to the power t over 4. So this is our model, and the question is now asking after how many hours will the bacteria count reach 1 million. So in other words, it's saying when n is t 1 million, what is t? So we will replace or plug in 1 million for the n here. So we get 1 million, which means 6 zeros, equals 1000 times 2 raised to the power t over 4. Now remember, this 1000 is being just multiplied with 2 raised to t over 4. We cannot multiply this 1000 with the 2, or we cannot multiply this 2 with the 1000, because the 2 has some power which 1000 does not have. So in order to get t, it looks like we have to convert to logarithmic form, but before we could do that, we have to get rid of this 1000 in front of our exponential function. So we divide by 1000 on both sides. Okay, so what are we left with? On the left hand side we will be left, so these 3 zeros and these 3 zeros cancel out, so we are left with still with 3 zeros on the left, 1 and 3 zeros, 1000 equal to, now this will be 1000 over 1000, so we will be left with 2 raised to the power t over 4. So what do we do now? We will take log on both sides. Why log? Because we have the 1000 here. So 1000 is a multiple of 10. So it will simplify things for us. So I take log of 1000 equals log of 2 raised to the power t over 4, which is going to be, so actually let's do it in the next line. So this one on the left hand side, because 1000 is what, 10 cube, so I can write it as, so this will be 10 to the 3 is equal to, now when we take log on right hand side, the power can come down here, and then we have log of 2. Now what is log of 10 to the 3? That will be just 3. So we have 3 equals t over 4 times log of 2. We simplify that, so we multiply by 4 and then we divide by log 2. So we get 3 times 4 is 12. 12 over log of 2 equals t. And that is our answer. So after how many days? After how many hours? So the population will be, or bacteria count will be, bacteria count will be 1 million after 12 over log of 2 hours. That's how you write your final answer. Okay, so you are not supposed to, of course you cannot, because on the exam you are not allowed calculator. So you will leave your answer as it is. This is what we say the exact form. Because if you take a calculator and plug in, you will get an approximate. You will have to round off, and that will be approximate. But if you have to, if you are allowed to use the calculator, then let us see what this number gives. So I have, let me turn on my calculator. So I will get 12 divided by log of 2. So I am getting one more time, just hold on. 12 divided by log of 2. So I'm getting 39.863. So the approximate value of this is, that's after doing the, here I should write it here, T is equal to 12 over log of 2 is coming out to be 39.863. Okay, now remember, when we approximate values, then we shouldn't round off after decimal places, because you cannot have like half a bacteria or 0.6 or 0.8 bacteria. You cannot have. So we round down. Okay, we round down. So if in the number you will say we have about 39 bacteria. Because I think in WebAssign, in the online homework, they ask you to take the calculator and find the value, approximate value. So about 39 bacteria. Okay, so now note here that this equation 1 that we have up there, we are raising 2 to the power of t, or t over, this is the equation 1. So we have the exponential function 2 to the power of t. We are using that function. Okay, so now can we have a different rate? Yeah, of course, because in that one we are using the population of bacteria which doubles every time or every day. But what if there is some other rate? Then if the base of the exponential function will change. So in general, we say, when we talk about an exponential function, or when we mention exponential function, we mean something like this. So initial population or initial amount times e to the RT. So remember, what is e? E is the irrational number, which is approximately equal to 2.7182, and R is called the rate of increase of the population. Now you can use any name for the function. So usually we will use this one for population and this for any other quantity, and you will notice that we often use this one for the decay model, because the decay model is going to be very similar. There is the only difference is that there the rate is of, we are getting rate of decrease, not increase. Okay, so let's look at the next example. So it says the general function a of t is equal to a sub 0 e to the RT. So like as I just mentioned, so you can have P, you can have Q, you can have A, you can have B, C, whatever. So we say that this function is used to model the amount of money contained in a 401k account, where the time t is measured in years. So you have to keep that in your memory. So suppose the account initially contains 8,000. So initial amount means A naught is $8,000. So after 7 years, the account has grown to, so we can say when t is equal to 7, A is equal to the amount A this side. Okay, the A is now 14,000, which is actually, if you note, this is the amount at after 7 years. What is the relative growth rate for the account? So the relative growth rate here is the R. Okay, so we want to find out R is equal to question mark. Because we already know what is A naught, so we can write our formula as A. Now we can ignore the T, or you can just say A is equal to 8,000, because that is the initial amount, times e to the RT. Okay, so we can say, okay, our formula is reduced to something like this. Now I will use this information and plug in. So how will it go? This is over here. For A, I will put 14,000. So this will remain as it is. E will be there. R will be there because that's what we want to find. But T will be replaced by 7. Okay. So now what happens? Or what do we do next? So the next step is that we divide. So always this will be done like these questions will be done in this manner. Next step would be to divide by the initial amount. Okay, so when you do that, on the right hand side, 8,000 over 8,000 is just 1, and up there we have e to the 7r, and on the left hand side we have 14,000 over 8,000. Okay, so which reduces to 14 over 8, which reduces to, so what goes in both? 2. So we have 7 over 4 equals e to the 7r. Okay, so now from here we have to get r, remember. So how do we do that? We will now take ln on both sides. Is that clear? Why do we take ln? Why not log? Because our base is e. Okay, because our base is e, therefore we are going to take ln on both sides. So we get ln of 7 over 4 equals ln of e to the 7r. Okay, so ln of 7 over 4 is equal to, so what happens is the 7r comes here and we are left with ln of e. But what is ln of e? Ln of e is 1. So we get ln 7 over 4 equals 7r. So how do I get my r now? I just divide by 7 on both sides. So r will be equal to 1 over 7 times ln of 7 over 4. So this is how you can leave it. So you can say rate, the relative growth rate, that's what R is called. Relative growth rate is 1 over 7 times ln of 7 over 4. Or we can do one more thing here. We can write ln of 7 over 4 as, so 1 over 7 outside, so we can ln of 7 minus ln of 4. So R is equal to, so now you can say relative growth rate is 1 over, or you can just say ln of 7 minus ln of 4 whole divided by 7. That's how you do this one. Okay, let's look at one more example. So this is about radioactive decay. Now, why we use it like that? Because often we have the radioactive substances, if left any place where you leave them, they are always decaying. They are, their mass is decreasing. So the rate of decay, we say, is proportional to the mass present or amount present, and that gives us this exponential model for that decay, or the decay model. So we say, the question says, so I believe this is example number 3. So it says a radioactive substance decays according to the formula Q of T equal Q naught e to the KT. The half-life of this substance is 10 years. What is half-life? So half-life is the time in which the radioactive substance amount, or the amount of radioactive substance becomes half of the original amount. Okay. So half-life, let me write the definition of half-life. Half-life, the time in which a radioactive substance becomes half the amount, half of the original amount. Okay. So we know that the half-life is 10 years. So in 10 years, it will become half of what it was. So the question then continues, if 200 grams are on hand initially, so initially if we had 200 grams of the radioactive substance, how long will it take for the amount left to be 25 grams? Okay, so you can do it actually without can you do it without the exponential? I don't know. Let's see. Okay, so we have Q of T equals Q naught. Now Q naught is given, it is 200 initial amount, e raised to the power kt. So remember, the first thing we do, although now this question is not in parts, right? Remember in the previous example, the first thing we did was find the model for that problem. So that is what we are going to do here. We have to find a model, exponential model for this problem, and then we will find whatever the question is asking. So in order to find the model, we will use the information that is given to us. For example, the half-life of the substance. Okay, so now this is what we have right now. Now we know that half-life (10 years). So what does that mean? It means when t is equal to 10, q is 100. That's what it means. So when t is equal to 10 years, Q will be equal to 100 grams. So we plug in. So 100 is equal to 200 e to the 10k. Is that clear? 10k or k10, right? It's because the k will stay, the 10 goes in for t. So actually it becomes k times 10, which is same as 10 times k. What is the next process? Always divide by this amount, both sides. So on the left hand side I get 1/2. On the right hand side I have e to the 10k. What do I do next? I will take the log on both sides. Which log? The natural log. So ln. So ln of 1/2 is equal to in other words, ln of 1/2 equals 10k, just 10k, because you are getting 10k ln of e, and ln of e is 1. So if someone wants to write it like this, that's fine. If you want to go ahead and do this step and then say ln of 1/2 is 10k, that is also fine. But also note here that this side, left hand side, ln of 1/2, so if you recall the graph of the function, it will be something like this. So if we have I'm talking about the graph of ln of x. So 1/2 is over here. So can you see that it will have a negative value? So this side will have a negative value, left hand side, so that k will become positive. So ln of 1/2 is equal to 10k. That's what I have right now. But this side will give me a negative number, this side. If you plug it in your calculator, you can see also, you can look at it in another way. So left hand side can be written as ln of 1 minus ln of 2. But ln of 1 is 0. So this quantity is 0. So I am left with negative ln of 2 is equal to 10k, or k is equal to negative 1 over 10 times ln of 2. So ln of 2 will be a positive number, but k is a negative number. Okay, now we take this k and plug it in our equation here. Therefore q of t is equal to 200 e raised to the power. Now if you leave it like this, if you get the k like 1 over 10 ln of 1/2, if you take this value and plug in here, that's fine. That is fine, you can do that. But just to show you that in the case of decay, this rate is negative, okay, because it's a rate of decay. So the thing is coming down, the amount is coming down. So I can write 200 times e to the 1 over 10 ln of 1/2, if I am using this quantity, times t. So that is going to be our model. Or if you got this one, then you will say q of t equals 200 e to the negative ln of 2 over 10 t. So this is the model. We are not done yet, okay? This is the model. We now, once we have the model, then we can answer any question about the problem. So it's as if how long will it take the amount to be 25 grams? So it's asking you in what time will it be 25 grams. So now we need to do t is equal to question mark when q is equal to 25 grams. So what do we do now? In place of q in the model, we plug in 25 and then is equal to 200 times e to the, so let's say you are using the first one, this one. So 1 over 10 ln of 1/2 over times t, because t is what we have to find. So how do we progress, or what is the next step? Always divide by this quantity. So left hand side, this gives me 1. So on the right hand side I will have 1 over 10 ln of 1/2 times t, and on the left side 25 over 200 will be 1 over 8. Okay. So now what do we do next? We take ln on both sides. So ln of 1 over 8 is equal to ln of this whole quantity, which will give me, so this left hand side will still be ln of 1 over 8 equals 1 over 10 ln of 1/2 times t, then ln of e, which is 1, so you can just leave it there. Now what to do? Now we have to divide by this whole thing, so that t will be equal to 10 times ln of 1 over 8 divided by ln of 1/2. Can we simplify this? That's the next step. Can we simplify this? So think about it. Notice that 1 over 8 can be written as 1 over 2 whole cube. So that the ln of 1 over 8 can be written as ln of 1 over 2 whole cube, which is equal to 3 times ln of 1/2. So this quantity ln of 1 over 8 replace it by that. Now this and this quantity cancel out and we get 30. So it will take 30 years to become 25 grams. So this is how you guys can do these problems. Yeah, basically the process you have to remember. When you plug in, then what number you have to divide by, and then once you do that, then it becomes easier to see that you have to now the question is now in exponential form, and you can apply the ln on both sides, or log, or whatever the base is, the logarithm of to the base, whatever the exponential base is. So hopefully you guys can do the problems now.